afternoon. It's very nice meeting all of you here, and especially I'd like to thank organizers to make me here and then give a chance to make this talk. So today I'm going to talk about emergent metric from T-type superconductor model.
This way, isn't it? This should go like this.
Okay, right there.
It's okay, don't worry. This way.
It's very uncomfortable.
Maybe more. Okay. Is it fine or not?
Like this? Okay. I
Only your pockets.
Okay. It's okay? Okay. Okay, today I'm going to talk about emergent metric from T-type superconductor model. And this work is in collaboration with Ki-seok Kim. He is a professor in the post-tech, and then working in the condensed matter theory. And then the Chan-young Park at the APCTP, he's a professor, and then working on high energy physics, string theory. So this is the motivation. So what was the motivation to working on this? So in high energy physics, we have a fundamental questions. So what is the nature of space-time? So far, we discovered some. Firstly, black hole thermodynamics. The 1970s, people came up ideas and then found out the black hole systems is quite similar to the thermodynamical systems, except the entropies. In the black hole space-time entropy proportional to the area, but ordinary thermodynamical system entropy proportional to the volume, except that is quite have a very similar structures. And then actually there was also study the similarity of the RNA-gas black holes and then van der Waals gas at a critical point. This study was done in these papers, and then in this study, the people identified cosmological constant as a pressure, and then the conjugate variables becomes the volumes, thermodynamic volumes of black holes. And then they found out the PV over T is equals 3/8. The value is the same as the van der Waals gas at the critical point. This is a very interesting result. And then another interesting one is ADS-CFT, which is the application of ADS-CFTs. Actually, in this study, people, charged RNA-gas black holes can have hairs, complex scalar hairs, and then the complex scalar hair at the boundary make some condensations. So then condensations is behavior similar like all the parameters in the second phase transitions. And then on top of it, people found out some transport coefficient, and then quite have a very similar behaviors with the superconductor system or metal systems. So actually from this, actually we don't know why, but actually we can see the black hole system is quite similar to the many-body systems. Then how about this? Can we construct a space-time from many-body systems? Okay, so let's try. This is the one of our motivations. Then how about the condensed matter physics? In condensed matter physics, as you know, there are many strongly correlated systems, but the mechanisms is not yet known for many cases. So then we can expect, could it provide a new tool to study, investigate those systems? So those are motivations for our study. Okay, let me explain our approaches. Basically, we started from the d-dimensional field theory and then construct the d+1 dimensional bulk space-time. So in order to that, we started with a transverse Ising model. Then why a transverse Ising model? Why we study with this model? Because it's simple. No interacting terms, but it describes superconductors. And then this model is known as Kitaev superconductor model. So basically what we did is this. Extract a metric structure from Kitaev superconductor model by performing the RG process, where the RG solution for a coupling parameter induces background spacetime to be curved. Okay, so this is the basic procedures. So I cannot say, this procedure is perfect, but we are working on it. So firstly, we map the transverse field Ising model to the Kitaev superconductor models, and then do real space renormalizations. And then by this process, we obtain RG equations for coupling parameters, and then and then we repeat this RG process several times. Then identify the number of repetition of RG transformations to the extra radial direction. And then plug RG solution for coupling parameter to the partition functions. Okay, so this is one steps. And then, the other hand, we write their equations in a curved spacetime in 2 dimensions. And then embed 2-dimensional spacetime to 3 dimensions. And then we compare these steps and then these steps. And then we extract the spacetime structures. Okay, let me briefly explain you the Kitaev superconductor models. So this is the transverse Ising models. This is the Hamiltonian, and then the sigma is the spinor. And then J is a ferromagnetic coupling constant, and the lambda is a transverse magnetic field. So actually, this fact is very well known. This Hamiltonian has a G2 symmetry, and then shows a quantum phase transitions at 0 temperatures. So if lambda is smaller than lambda c, then this describes a ferromagnetic phase, and if lambda is bigger than lambda c, then it describes a paramagnetic phase. Actually, but this is not our interest. So actually, in 2000, Kitaev published a very interesting papers. He started with these transverse Ising models, and then he made these Jordan-Wigner transformations. So basically, Jordan-Wigner transformations map the spinor to the fermions. So this is the spinor field, and then this is the spinors fermion field. So actually, the spinors on the side to side, if we change the 2 spinors on the other side, then they commute. So actually, this map kind of, allows so we can just identify spinor to fermions. So this Jordan-Wigner transformations make the spinor to the fermions, which is commute with the another side. Okay, so if we employ these Jordan-Wigner transformations, then this Hamiltonian changed to in this form. Okay, then now let's do the Majorana decompositions. So if we identify this is one Majoranas and the other, then the Hamiltonian can be written in this way. Okay, let's take a look. So if the T1 is bigger than T2, if this term is dominant, then the Majorana fermion, this is the one side. Each side we have 2 Majorana fermions. So if T1 is dominant, then on the same side, the Majoranas are pairing. There is a Majorana pairing on the same side. See gamma 1 and gamma 1. So they are paired on the same side. On the other hand, if this term is dominant, then there is a pairing on the other side. The Majorana fermions have a pairing with the other side. So actually, this describes a strong pairing phase, which is trivial superconductors, but this phase describes weak pairing phase, which is topological superconductors. So why topological superconductors? As you can see, at the end of the edge, which is the boundary of material, there is a fermions, Majorana fermions unpaired. So actually, this make the topology non-trivial. So in this phase and this phase is topologically distinct. So this is basically the idea of Kitaev's, and then actually this idea is draw many attentions because he kind of shows how the Majorana fermions can be appears in the condensed matter system. Okay, so let's do let me introduce our work. So we employed a number spinor representation like this. So the Ci, as I mentioned, is spinless fermions, and then we rewrite the Hamiltonian in terms of the number spinor representations. Then this is the partition function. Okay, so if we perform the renormalization group transformations, then after if we do this k-1, then this is that. Okay, step is like this. Firstly, separate the site into separate the site index into even and odd. And then second, perform the Gaussian integration for odd site. And third, rescale the fermion field to reproduce the original lattice. So okay, step is like this. Okay, so from the partition functions after k-1 Rayleigh transformation, let's redo it. So separate the index even and odd. So even and odd, even and odd. We separated index. And here we integrated out the odd side. So we only have the even side. And then now we rescale the fermion field. And then let's compare two partition functions. If we change k-1 to k, then we can compare two partition functions. Then we can obtain RG equations like this. So this is the coupling constants after kth RG transformations, and then this is coupling constant after k-1 the RG transformations. And then this is the original value of J and lambda. So if we do some manipulations like this, and then this allows us to go to the continuum limits. So and then this expression we can change to the differential equations. And then we can obtain the solution of these equations, and then plug this to the partition functions. Then this is the IR effective action we obtained. So initially we had a partition function in this type. And then by plugging the RG solution on the coupling constant, we could obtain these effective IR actions. Oh, I? This I? Oh, we see. This one. Sir? Which summation? Okay. Oh, this I. Yeah. Okay, sorry. We went to the continuum limit. So we went to the continuum limits. So we changed the I index, changed it to the X. Yeah. Thank you. Yeah. Okay. So this is the one step. And then let's think about so this is another story. Okay, let's write the Dirac equations in 2 dimensions. So and then in curved space-time. So we're gonna consider this type of the metric, curved space-time. And then this is the Dirac equations in the curved space-time. Okay, then let's compare these Dirac equations with this effective action. Then what we can do is we can determine what A and B. This is the metric component A and B. Okay, then now let's embedding this 2-dimensional metric to the 3-dimensional space-time. So now we additionally have a new coordinate, which is lambda. Sorry, this is lambda, and then the metric component is C. So C is not yet determined. Okay, then now so actually this is the value for A, this is for value B. And then we're gonna take the exponential lambda becomes R. So and then we're gonna we're gonna make a choice. So y becomes minus 2 lambdas. So you will see why we made this kind of choice. So as I can see, this A and B could be read from the previous effective actions. So this is A and this is B. So by imposing this condition, we could read of this GRR component. Okay, so the metric is determined in this form. Okay, so as I mentioned, depending on the lambda, it describes the different phases. So if lambda is bigger than 2, then that describes the just superconductor, strongly coupled superconductor phase, and the lambda is smaller than 2, it describes the topological superconductors. So for simplicity, I changed the variables lambda minus 2 equals lambda prime. Okay, then let's take a look at quantum critical point. So if we identify like this, and then if lambda goes to critical value of 2, then this is the metric. So this is nothing but the ADS space-time. So yesterday, the Gia-Debali identified the quantum critical point with black holes, but now today, we identified quantum critical point with ADS matrix. And then, okay, let's take a look on the regions of lambda. So lambda prime is bigger than 0, and then this describes non-topological phase, and then if lambda prime is smaller than 0, it describes topological phase. So and then if we take R equals infinite limit, then the metric becomes asymptotically flat. And then let's look at the Riemann curvature squares. So this is a Riemann square curvatures. So as you can see, if lambda is smaller than 0s, then it has curvature divergence. So in this case, which is the topological superconducting phase, we became to have a naked singularity. Okay, then let's check the Einstein equations. Since in the non-critical point, if lambda is bigger than 2 or smaller than 2 case, the metric structure asymptotically flat at R equal infinity. So we can employ the Einstein equations like this, and then plug the previous metric into these Einstein equations. We can read of the meta components T, R, T, X, X. So as you can predict, we have negative energy density, negative energy, and then pressure, the positive pressures. This is not physical, but yep. Okay. Summary. So we constructed an emergent space-time from Kitaebu superconductor model. And then the emergent space-time description for Kitaebu model could be on all the parameters for topological phase transitions we expect. Actually, in condensed matter, we have a topological superconducting phase and non-topological superconducting phase. So in that case, the topological properties can be all the parameters. So for example, people calculate the Papians, something like that, and then people consider that kind of things all the parameters. So here, as I showed you, in the topological superconducting phase corresponds to the space-time with naked singularities. So we expect this kind of properties. So the space-time has this kind of properties. So we can consider the gravity descriptions. This emergent space-time could provide us some, how to define all the parameters of two phases. Okay, then future work. Actually, by repeating the algebra process, we identify the number of repetitions to the extra dimensions. But actually, there was some artificial process. Actually, we just imposed our component to be to become ADS metric at the critical point. So, but actually, we are trying to find out a way to have a constraint on radial component. Naturally have an ADS metric at the quantum critical point. And then how to characterize topological property for space-time having a naked singularity, which is lambda smaller than 2 cases. So we have a naked singularity space-times, but I don't know yet how to characterize topological properties, how to calculate the space-time in the topological number or something. And then actually we don't know yet the dictionaries between field theory and bulk structures. Actually in holography, the holographic dictionary is well established. So we can have a correspondence. Okay, this is a field, we have a bulk system, and then this bulk system describes some field descriptions. But actually we don't know yet the dictionaries between field and the bulk. So actually, we are working on the OM vector models and then Kondo models, some other condensed matter models. So we are not sure yet what we can get out of this study, but we are working on it. Okay, thank you.